There is a specific moment when space stops being merely distant and becomes something else. Not just large, not just empty, not just cold, but qualitatively different. As though the rules by which the universe operates begin to change the further you move from everything familiar. This is not a metaphor. The further you travel from Earth, the more hostile the environment becomes. Not linearly, not gradually, but in steps, each next threshold bringing a completely new category of threat that did not exist of the previous one. Each next scale, a different kind of thing that can kill you, destroy your ship, or simply make the very concept of getting there impossible. And there is a point, very far, beyond anything we have ever visited or plan to visit in the foreseeable future, beyond which space stops being merely a place where you feel bad and becomes a place where the very concept of existing begins to break down at the level of physics. Tonight we are going to travel that journey honestly, not as a list of frightening facts, but as a real investigation of how the nature of the threat changes as you move outward, from low Earth orbit to the Moon, to the outer planets, into interstellar space, into the intergalactic void, and beyond, to places where the physical laws operate in regimes that are difficult even to describe. Each threshold, its own kind of horror. If the night is long, stay. Let us begin at the first threshold, low Earth orbit, and with what makes even the most basic step into space fundamentally different from any experience on the surface. The International Space Station orbits at about 400 kilometers altitude. This sounds far, but in the scale of Earth itself, it is almost nothing. Earth's diameter is about 12,742 kilometers. 400 kilometers is roughly 3% of Earth's radius. If Earth were an apple, the ISS would be orbiting at about the distance of the apple's skin from its surface. And yet, already here, at 400 kilometers, the environment is lethal in several independent ways. Vacuum. Outside the ISS, the pressure is about 10 to the negative 14 atmospheres. This is so close to absolute vacuum that the difference has no practical significance. A human without protection in vacuum loses consciousness in about 15 seconds. Not from explosion, skin is strong enough to contain the pressure of blood and tissue, but simply because the lungs stop oxygenating the blood. Irreversible brain damage in 4 to 5 minutes. Temperature. In the ISS orbit, surface temperature depends on illumination. On the sunlit side, up to plus 120 degrees Celsius. In shadow, down to minus 160 degrees. A swing of nearly 300 degrees depending on orientation to the sun. The only thing standing between astronauts and this is the suit and the station's hull. Radiation. At 400 kilometers altitude, the ISS is still partially protected by Earth's magnetosphere. Astronauts receive about 150 to 200 millisieverts per year, 50 to 100 times more than a person on the surface. This is significant but manageable. NASA's career limit is about 1,000 millisieverts. Debris. About 27,000 tracked pieces of orbital debris, rocket fragments, non-functional satellites, collision remnants. At orbital speeds, about 7.7 kilometers per second for the ISS, even a paint fleck 1 centimeter across carries kinetic energy equivalent to a hand grenade. The ISS has specialized protection against small fragments, but maneuvers to dodge larger ones. This is the first threshold, 400 kilometers. Already here, any loss of protection is lethal within seconds or minutes. Already here, the human body without technological support exists for no more than a few minutes. But this is still the gentlest of all the thresholds. Here we are still in the rescue zone, where evacuation to Earth takes hours. Let us now talk about the next threshold, the Moon, and about what qualitatively changes when you exit Earth's magnetosphere. The Moon is, on average, 384,400 kilometers from Earth. The Moon's orbit passes through Earth's magnetotail, the long magnetic wake stretching away from the Sun. But most of the time, the Moon sits outside the magnetospheric bubble. This is a fundamental transition. On the Moon's surface, there is no magnetic field in the Earth sense. There are residual, locally magnetized patches of crust, but they create no global protection. And there is no atmosphere. These two facts combined mean that the lunar surface is exposed to everything that flies from space, directly, without filter, without shield. Radiation on the Moon. About 380 millisieverts per year under normal conditions. Almost twice as much as on the ISS. This happens because the ISS is still partially shielded by the magnetosphere. The Moon is not. But the main problem is not the baseline radiation level. The main problem is solar flares. During a powerful solar flare accompanied by a coronal mass ejection, radiation intensity at the Moon can increase hundreds to thousands of times. The dose received by an unprotected person on the lunar surface during a major solar proton event can be lethal within hours. During the Apollo program, this was a genuine risk. If a major solar flare had occurred during one of the lunar expeditions, the astronauts on the surface would have received a dangerous dose. Calculations show that a major event between Apollo 16 and Apollo 17 in August 1972, had it coincided with a surface excursion, could have been lethal. We simply got lucky. Another feature of the lunar surface that many people underestimate: lunar dust. Regolith on the Moon consists of sharp angular particles. Unlike terrestrial dust, which rounds with time from friction, lunar regolith keeps its sharp edges because there is no wind or water to smooth them. The dust is electrostatically charged and clings to everything. Apollo astronauts found that lunar dust penetrated everywhere, into suits, into equipment, onto instruments. It is abrasive and potentially toxic when inhaled. Harrison Schmitt, the only geologist to walk on the Moon, experienced what resembled an allergic reaction to lunar dust already on the return capsule. Long-term inhalation of lunar regolith is a genuine medical threat for future lunar bases. Let us now talk about Mars, the next threshold, and what is fundamentally new at a distance of 55 to 400 million kilometers, depending on orbital positions. Mars adds to radiation and vacuum threats something fundamentally new: the impossibility of rapid evacuation. On the Moon, in case of emergency, return to Earth takes about 3 days. This is long by earthly standards, but medically it is still within the range where many critical conditions can be stabilized for 3 days. Mars at closest approach, about 55 million kilometers. At greatest separation, up to 400 million kilometers. Minimum travel time using current technologies, about 6 to 9 months one way. And this is not merely a delay. Windows for flights between Earth and Mars open only once every 26 months, when the planets are in favourable relative positions. This means if something goes wrong on Mars, you cannot simply go home. You must either wait for the next window, up to 26 months, or return at a non-optimal time with enormous additional fuel cost. Mars's atmosphere is about 1% of Earth's by pressure. It consists primarily of CO2. It cannot be breathed. It provides no meaningful radiation protection. It creates no significant thermal barrier. Dust storms on Mars are planetary in scale. Periodically, roughly every few years, a storm can envelop all of Mars and last from several weeks to several months. In 2018, a global dust storm killed the Opportunity rover, cutting off sunlight to its solar panels. For a crewed mission, a global dust storm lasting months would block all planned surface operations, disrupt solar panel function, and create extreme psychological conditions for a crew locked inside a habitat with no ability to go outside. Temperature on Mars ranges from about plus 20 degrees at the equator in summer noon to minus 125 degrees at night at the poles. Average surface temperature about minus 60 degrees Celsius. Mars adds to physical threats a new category: psychological isolation with complete absence of a way home in any reasonable time frame. This is qualitatively different from the Moon. Communication with Earth on Mars, delay from 3 to 22 minutes one way depending on planetary positions. Real two-way dialogue is impossible. Any medical consultation with Earth takes 6 to 44 minutes per question and answer. Let us now talk about the next qualitative leap, the asteroid belt and the outer planets, and about what fundamentally changes when you move beyond 5 astronomical units. At 5 astronomical units from the Sun, Jupiter's distance, sunlight is 25 times weaker than at Earth. This is not yet darkness, but it is no longer the illumination we think of as daylight. More importantly, at 5 astronomical units, the Sun's heliosphere still shields from galactic cosmic rays. But the protection is weaker than at Earth. Solar wind density at 5 astronomical units is roughly 25 times lower than at Earth, decreasing proportional to the square of distance. Jupiter itself generates the most intense magnetic field of any planet in the solar system, roughly 20,000 times stronger than Earth's. Its radiation belts are one of the most hostile environments in the solar system. The orbit of Europa, Jupiter's icy moon considered one of the places of potential life, lies in a radiation zone so intense that an unprotected human there would receive a lethal dose in about 10 minutes. To work near Europa, significant radiation shielding is required. Any probe or spacecraft must be specially hardened against radiation damage to electronics. This is why the development of Europa Clipper required specific engineering solutions for radiation resistance. At Neptune's distance, 30 astronomical units, sunlight is 900 times weaker. The Sun is no longer a disk warming your face, it is simply a very bright point. Temperatures in the upper atmospheres of Uranus and Neptune around minus 200 degrees Celsius. Neptune was discovered in 1846. Only one spacecraft, Voyager 2, has visited it in 1989. That was 35 years ago. There is no planned mission to Neptune in the next 20 years. This says something important, not only about the difficulty of such missions, but about how fundamentally far these places are from our ordinary experience. Let us now talk about the next threshold, the heliopause, and what happens when you leave the protective bubble of our star. The heliopause is the boundary where the solar wind, the stream of charged particles emitted by the Sun, stops against the pressure of the interstellar medium. Voyager 1 crossed it in 2012 at about 121 astronomical units from the Sun. Voyager 2 in 2018 at about 119 astronomical units. What changes beyond the heliopause? Inside the heliosphere, the Sun creates a protective bubble. Interstellar galactic cosmic rays, charged particles accelerated to relativistic speeds by supernova explosions and other catastrophic events in the galaxy, are partially deflected by this bubble. Inside the heliosphere, the dose of galactic cosmic rays is significantly lower than outside. Beyond the heliopause, the heliosphere's protection disappears. Full flux of galactic cosmic rays. Voyager 1's data after crossing the heliopause showed a sharp increase in galactic cosmic ray dose, roughly 3 times by some components. This confirmed theoretical predictions about the protective role of the heliosphere. But what specifically makes this threshold horrifying? Galactic cosmic rays are not the same as solar radiation. They are primarily protons and nuclei of heavy elements, carbon, oxygen, iron, and heavier, accelerated to energies of billions and trillions of electron volts. At such energies, they penetrate almost any material. Lead shielding, standard protection against radiation in earthly conditions, does not work against high-energy galactic cosmic rays. Worse, when high-energy protons interact with heavy lead nuclei, secondary particles are produced. A thick layer of lead can increase the dose rather than reduce it. The best protection against galactic cosmic rays: hydrogen-containing materials. Water, polyethylene. Hydrogen has the smallest nuclear mass and produces the smallest amount of secondary radiation. But even 50 centimeters of water around a living module is an enormous additional mass. And the main point, no practically achievable layer of passive shielding completely stops high-energy galactic cosmic rays. They are too high energy. They pass through everything. Beyond the heliopause, in interstellar space, any crew is exposed to a radiation dose that with prolonged exposure significantly shortens lifespan and elevates cancer risk. This is not instant death. This is the slow accumulation of biological damage that cannot be completely prevented. Let us now talk about what this radiation specifically does to the brain, because this is the most disturbing and least discussed specific mechanism. Neurons, the primary cells of the brain, do not divide. Unlike most other cells in the body that can replace damaged cells through division, neurons mostly exist for the entire lifetime. Lost neurons are generally not replaced. This means radiation damage to neurons accumulates without the same degree of recovery as in other tissues. Studies conducted by NASA on mice showed that exposure to simulated galactic cosmic rays causes cognitive impairment, including memory deterioration, reduced learning ability, and behavioral changes. This is connected to damage in the hippocampus, the brain region critical for memory, and in the prefrontal cortex, responsible for decision-making and executive functions. A study published in 2016 by Charles Limoli's team at the University of California showed that even relatively low doses of radiation simulating interplanetary flight conditions caused persistent cognitive impairment in mice. 6 months after exposure, the mice still showed signs of memory impairment and heightened anxiety. For a Mars mission and back, about 3 years total flight, the accumulated dose of galactic cosmic rays may cause measurable decline in cognitive functions. Not acute, not sudden, but gradual deterioration that accumulates over months and years of flight. An astronaut returning from a 3-year Mars mission may have slightly worse memory, react more slowly, process complex information less well than when they launched. The difference may be small, but it will be real, and it will be permanent. For interstellar flight, with significantly higher doses of galactic cosmic rays beyond the heliosphere and without sufficient shielding, the cognitive damage would be significantly more serious. A crew arriving at another star may be cognitively impaired compared to what they were when they departed. This creates a profound irony. The only way to reach another star, to travel through an environment that gradually damages precisely what makes this journey meaningful. The mind that wants to know another world is gradually damaged by the very journey toward it. Let us now talk about something that happens at interstellar velocities that has no analogue in any inner solar system travel, about what interstellar dust becomes when you hit it at relativistic speed. Interstellar space contains rarefied gas, primarily hydrogen and dust. The average density is very low, about 1 hydrogen atom per cubic centimetre. This is essentially perfect vacuum by earthly standards, but at 10 to 20% of the speed of light, even a single hydrogen atom becomes dangerous. At 0.2 C, 20% of the speed of light, A hydrogen atom colliding with the front surface of a ship carries kinetic energy roughly comparable to an X-ray photon. At interstellar gas density of 1 atom per cubic centimetre, in 1 second of flight, the front surface of a ship 1 square metre across encounters about 60 million hydrogen atoms. This is a flux of ionizing radiation, growing with each hour of flight, gradually eroding the materials of the ship's forward surface. Dust grains, ranging from fractions to several microns in size, at 0.2 C, carry kinetic energy equivalent to a small explosion. For a tiny nanocraft like Breakthrough Starshot envisions, a single dust grain of a few microns is a catastrophic event. For a full-scale crewed ship at 0.2 C, structural damage from dust erosion over 20 years of flight would require specific protective measures. A thin shield of hydrogen-containing material on the ship's nose, the dust shield concept, is one of the proposed solutions. But here is what makes this particularly unsettling. The shield erodes. Every dust grain that hits it removes some material. Over 20 years of flight at 0.2 C, the shield thins. At some point, the protection is insufficient, and there is no way to replace the shield during flight. You launched with what you have. What erodes stays eroded. Let us now talk about the intergalactic void, the next threshold, and why it represents a qualitatively different category from everything before it. The nearest large galaxy to the Milky Way, the Andromeda Galaxy, M31, is about 2.537 million light-years away. The distance to it is 600,000 times the distance to Proxima Centauri. The space between galaxies, the intergalactic medium, is the emptiest place in the universe. The average matter density there is about 1 hydrogen atom per 10 cubic meters. This is 10 billion times less dense than the interstellar medium inside a galaxy. No stars, no planets, no dust clouds, no anything. The only thermal radiation that permeates intergalactic space everywhere, the cosmic microwave background, the residual glow of the Big Bang. Its current temperature, about 2.725 Kelvin. This is the temperature to which any object in a completely dark place with no other heat sources will eventually cool, roughly minus 270 degrees Celsius. A ship stranded in intergalactic space cannot be rescued by anyone or anything. Not because a rescue operation is difficult, but because it would take millions of years just to deliver a distress signal. This is not the hostility of something trying to kill you. This is the indifference of a place where the very concept of rescue has no meaning. Not because no one cares, but because the geometry of the situation makes it physically impossible within any timescale that contains meaning. Interstellar space is dangerous. Intergalactic space is something stranger. It is the place where even danger becomes irrelevant because rescue becomes inconceivable. Let us now talk about something that is both the most abstract and the most inevitable of all the things that make space more horrifying the further you go. About the cosmological structure of the universe itself and what it means for travel. The universe is expanding, not because everything is flying apart in space, but because space itself is stretching. This distinction is fundamental. Because of this expansion, there exists a particle horizon or Hubble horizon, a distance beyond which objects are receding from us faster than the speed of light. The current radius of the observable universe is about 46.5 billion light-years. As you approach the edge of the observable universe, galaxies begin receding from you at speeds increasingly close to the speed of light. Their light becomes increasingly redshifted, frequency drops, wavelength grows. Eventually, at sufficient redshift, galaxies become invisible in the optical range. Their light has shifted to radio and then to even longer wavelengths. But here is what makes this concept truly strange. If you travel towards the edge of the observable universe, you approach your own particle horizon. Objects beyond your horizon cannot send you a signal. Their light will never reach you because the space between you is expanding faster than light moves. This is not a physical wall, it is a horizon. And, like the ocean horizon, it always remains at the same distance from you. You move toward it, it recedes. Wherever you fly, the observable universe will always have the same radius from whatever point you occupy. This means the concept of getting to the edge of the universe has no meaning. There is no edge. There is a horizon that follows you. And this is precisely what makes the situation more frightening rather than better. The universe does not have an edge you can reach. The universe continues infinitely beyond any horizon. And that infinity, filled with increasingly distant and increasingly inaccessible objects, continues without limit in every direction. Let us now talk about something that is the most personally immediate of all the horrors we have discussed, about what happens to the human body in weightlessness over sufficient time, and why this is a form of slow dismantling. The human body was designed, in the evolutionary sense, to operate under the constant gravitational field of 1g. Every system assumes this field. Bone. Bones bear load, the weight of the body. This load signals bone-building cells, osteoblasts, to maintain density. In weightlessness, the load disappears. Osteoblasts become less active. Bones lose mineral density at roughly 1 to 2% per month, primarily in load-bearing bones, hip, lumbar spine. After 6 months on the ISS, an astronaut can lose up to 10 to 15% of bone mass. Calcium from bones enters the blood and is excreted in urine. Kidney stone risk increases. Bones become more fragile. Muscle. Without load, muscles atrophy, primarily the postural muscles that support the body against gravity. In weightlessness, they are not needed for maintaining posture. Over 6 months without intensive countermeasures, muscle mass loss can reach 20 to 30%. ISS astronauts exercise 2 to 2.5 hours per day, a significant fraction of the working day, only to slow this process. Not stop it, slow it. The cardiovascular system. On Earth, the heart works against gravity, pumping blood upward to the brain. In weightlessness, this work disappears. The cardiovascular system adapts. The heart decreases in size, blood volume decreases. Upon return to Earth, the cardiovascular system cannot handle the sudden load. Blood pressure drops when standing upright, fainting in the first days after return. Every astronaut after a long flight needs assistance exiting the capsule. The vestibular system. The inner ear contains balance organs, otolith organs, that respond to gravity. In weightlessness, their signals no longer match other sensory inputs. The brain receives contradictory information. Result: space motion sickness. Nausea, vomiting, disorientation. Most astronauts experience this in the first days or weeks of weightlessness. Fluid in the body redistributes. In weightlessness, this doesn't happen in the normal way. Fluid moves into the upper body and head. Result: permanent facial puffiness, nasal congestion like a permanent cold, elevated intracranial pressure. This intracranial pressure presses on the optic nerve and on the back wall of the eyeball, changing the eye's shape. The result is a condition called spaceflight-associated neuroocular syndrome, SANS. A significant fraction of astronauts after long missions report worsening vision. Some changes do not fully reverse. Now imagine all of this simultaneously for 3 to 4 years, the duration of a hypothetical Mars mission, not 6 months on the ISS, 2 to 3 times longer. A crew member returning from Mars may have significantly weaker bones, significantly reduced muscle mass, a heart that has shrunk from disuse, eyes that see slightly less clearly than when they left. They paid for the journey not just in time and risk, but in their own biology. Let us now talk about the psychological dimension of deep space in more specific terms, about what prolonged absolute isolation does to the mind, and why this too is a form of physical damage. The human brain evolved in a specific environment, rich in sensory diversity, wind, temperature change, the sound of other organisms, the sight of varied landscapes, the smell of earth and plants. Rich in social context, other humans, communication, feedback, the sense of being embedded in a web of relationships. Space removes all of this simultaneously. On the ISS, 6 people in a metal structure smaller than a 6-bedroom house, circling Earth every 90 minutes, no fresh air, no outdoor spaces, no natural sounds, no privacy. The same faces every day, the same sounds, the hum of fans and pumps, the same smell, recycled air, for months. Studies consistently show that the critical variable in crew performance over long missions is not individual competence, it is group dynamics. A crew of 4 average performers with excellent interpersonal compatibility will outperform a crew of 4 brilliant individuals with interpersonal friction. Human relationships under extreme stress and confinement become the most important operational variable. The phenomenon called the third quarter effect is consistently documented across isolated environments, Antarctic winter rovers, submarine deployments, simulated space missions. Roughly 60 to 75% of the way through any long mission, psychological state is at its lowest. Motivation drops. Conflicts increase. Cognitive errors occur more frequently. For a Mars mission, this would fall roughly 18 to 20 months into 36. Several months after the initial excitement of landing on another planet has faded, with the return still more than a year away, in a habitat with no exit, with no rescue possible. And this is while simultaneously experiencing the bone loss, the vision changes, the cognitive effects of radiation, the circadian disruption from artificial light cycles, the nutritional limitations of stored food degraded by years of radiation exposure. These stresses do not add, they multiply. Stress suppresses the immune system. A suppressed immune system handles radiation-damaged DNA less effectively. Sleep disruption amplifies the stress response. The altered microbiome changes metabolism and nutrient absorption. The body's ability to repair radiation damage weakens. The cumulative load of a years-long deep space mission creates a biological and psychological burden that is not simply the sum of its components, but the product of their interactions. Let us now talk about the specific and rarely discussed psychological phenomenon of temporal isolation, about what a communication delay, measured in years, actually does to the experience of connection. On Earth, communication is instantaneous. You speak, the other person hears. You send a message, it arrives in seconds. Relationships exist in real time. On the ISS, delay is fractions of a second, still real time. On Mars, 3 to 22 minutes one way. Dialogue becomes exchange of monologues. You ask a question. You wait up to 44 minutes for a reply. This is difficult, but it still feels like connection. At 4 light years, the distance to Proxima Centauri, delay is 4 years one way. A question asked today receives an answer in 8 years. A conversation with a specific person on Earth is impossible in any meaningful sense. only exchange of letters with years of delay. In the time between asking a question and receiving the answer, your life has changed. The life of the person you wrote to has changed. People you addressed may have died before the reply arrives. The first generation of people on an interstellar ship still remembers Earth, personally. The second generation knows Earth only from parents' stories and messages arriving with years of delay. The third, only from history. They travel toward another star, but they simultaneously travel into the future. The growing distance in space is accompanied by growing distance in time. They arrive not just at another world, but at a moment removed from their departure by years or decades. This form of isolation has no name in our language because no one has experienced it. Let us now talk about what is perhaps the deepest horror of deep space. Not the most immediately dangerous, but the most conceptually final. About the heat death of the universe. The second law of thermodynamics states that entropy, the measure of disorder, in a closed system can only increase or remain constant over time. It never decreases spontaneously. The universe is a closed system, or at least we know of no external exchange with anything outside it. Therefore, the entropy of the universe increases. Every physical process, a star burning, a stone falling, your next breath, slightly increases the total entropy of the universe. The final state of this process, the heat death of the universe, maximum entropy, a state in which all matter and all energy are distributed uniformly throughout all space. No temperature gradients, no energy flows, no possible work or information processes. This does not happen quickly. It happens on timescales that make the word long meaningless. The last stars will burn out in about 100 trillion years, 10 to the 14th power years. All stars will have exhausted their fuel. What remains will be cooling white dwarfs, neutron stars, and black holes. Then, the era of degenerate remnants. White dwarfs slowly cool, gradually becoming black dwarfs, cold, dark objects. This takes roughly 10 to the power of 37 years. Then, black holes. They evaporate through Hawking radiation. A black hole of the Sun's mass evaporates in about 10 to the power of 67 years. A supermassive black hole at the center of a galaxy in about 10 to the power of 100 years. After the last black hole evaporates, the universe contains only relic photons and neutrinos, gradually losing energy in the expanding universe. Temperature falls ever closer to absolute zero. No structures, no processes, complete thermodynamic death. This is where the universe is heading. Not hypothetically, inevitably, by physical laws we understand with high confidence. The most distant horror of deep space is not a black hole or a gamma-ray burst or the radiation between the stars. It is this: the universe itself is dying, slowly, on timescales that dwarf any timescale with a name, but the trajectory is set. Entropy always wins. Every star that burns a little of the universe's remaining useful energy. Every process, every thought, every journey contributes to the final equalization. There is no way to stop this. There is no way to reverse it. There is only more time and less of everything that makes time worth having. Let us now talk about the single most important truth that connects all of these thresholds, about what each one reveals that is not obvious from Earth. Every threshold we have passed tonight is the negative image of something Earth provides without announcement. The magnetosphere we never notice until we are on the moon with a flare incoming. The atmosphere we do not feel as protection until we are in vacuum and our lungs have nothing to pressurize against. The gravity that calibrates every bone and muscle and cardiovascular system without our awareness until we are 6 months into weightlessness and cannot walk unassisted upon return. The 24-hour cycle that synchronizes our biology with rhythms we never chose, until there is no day and no night, and our circadian rhythm loses its anchor. The biosphere that produces oxygen, food, temperature regulation, functions so fundamental we have no word for their presence, only for their absence. The presence of other humans at a distance bridgeable in seconds, until the nearest response to any message takes years to arrive. Deep space removes all of this simultaneously, and the body built for a world with all of it begins, in different ways at different rates, to fail. This is the honest accounting, not presented to frighten, presented because honesty is the only foundation from which real understanding can grow. The people who will fly to Mars know these numbers. They will have sat with flight surgeons discussing each specific mechanism. They will have signed consent forms that describe the biological costs in plain language. They will have looked at the data from ISS missions, from the twin study, from the animal experiments on galactic cosmic ray exposure. And they will fly anyway. Because something in human nature, something that has driven us from the trees to the moon in a few million years, insists on going toward what is beyond the horizon, even when the horizon conceals something more dangerous than anything behind us. This has been true of every person who first climbed a mountain that no one had climbed, every person who first crossed an ocean that no one had crossed, every person who first entered an environment that everyone else said was too dangerous to enter. They went. They paid the cost of going, and everything we know about those places, everything we have built on the foundation of their knowledge, came from what they found. Deep space is the next such place, the most dangerous, the most honest about its danger, the most indifferent to our survival. And we are going there. Slowly, carefully, with instruments and suits and medications and shielding and psychological support programs and exercise machines bolted to the walls. But going, because this too is what we are. Let us talk about something that makes the horror of deep space more specific and more personal than abstract descriptions of radiation and vacuum, about what the experience of each threshold would actually feel like to a human being passing through it for the first time. The ISS astronaut's first spacewalk. You exit through the airlock. The hatch closes behind you. For the first time in your life, there is nothing between you and the universe except a few layers of material a few centimeters thick. On one side of that material, a pressurized environment kept at exactly the right temperature, with breathable air, with food and water, and other humans. On the other side, vacuum. Absolute vacuum. The transition is measured in centimeters. Most astronauts report that the first thing that strikes them is not fear, but scale. Earth curves below in a way that no photograph prepares you for. The blackness above is absolute. Not the dark blue sky of high altitude, not the deep blue of orbit photographs, but genuinely black. Black the way nothing is black on the surface. The Terminator, the line between day and night on Earth below, moves visibly. Stars do not twinkle because there is no atmosphere to scatter their light. They are just points, hard points. And it is silent. Space is famously silent because sound requires a medium. There is no medium. But the silence is stranger than that description suggests, because inside the suit you hear your own breathing, your own heartbeat, the hiss of air circulation. You are the loudest thing in an environment where nothing else makes any sound. This is 400 kilometers. Now move outward. Apollo astronauts leaving Earth orbit described the moment when the Moon's gravity began pulling them away from Earth as one of the most strange experiences of the mission. Not dramatic, not cinematic, but deeply unsettling in a quiet way. The Earth visibly shrinking over hours, becoming a sphere, then a disk, a marble. Buzz Aldrin described looking back at Earth from the Moon and seeing it as a beautiful sphere hanging in space, and feeling how small it was. Not intellectually knowing it was small, feeling it. The entire world of 3.5 billion people in 1969, every civilization, every war, every ocean, every mountain, a circle about the size of his thumb, held at arm's length. Edgar Mitchell, on the return trip from the Moon, had what he described as an epiphany while looking out at the universe, a sudden, overwhelming sensation of the interconnectedness of everything. He later called it a savikalpa samadhi, a term from Eastern philosophy for a specific kind of transcendent experience. He spent years afterward studying consciousness and the nature of this experience. The lunar experience changes people, not just as a biographical fact, but neurologically, perceptually, in the way they organize their understanding of scale and connection. Now imagine not returning. Imagine continuing outward, past the Moon, past Mars, where Earth is a bright blue star, not a disk you can recognize as home. Past the asteroid belt, past Jupiter, where the Sun is already visibly smaller, visibly less warm, visibly less overwhelming. Past Saturn, where the Sun is bright but distant, where the rings of Saturn stretch across the sky if you are orbiting it, where Titan's orange haze is visible from orbit, where the solar system still feels like a solar system, structured, oriented around something. Past Uranus and Neptune, where the Sun is simply a very bright star, not overwhelming, not a disk, a star. And around you, other stars. The Sun is brighter than all others, still clearly dominant, but it is in the same category as the stars. A point, not a presence. At this moment, somewhere around 50 to 100 astronomical units from Earth, something shifts. You can still point at the Sun and say that is home, but you can no longer feel it. You cannot feel its warmth. You cannot see it as a disk without optical aid. It is a point among points. This is a specific kind of loneliness that no human has yet experienced, and for which we have no vocabulary. Let us now talk about the psychological concept of salience, about how the human brain processes threat, and why deep space is so psychologically challenging in ways that are not immediately obvious. On Earth, dangers are mostly salient. They look dangerous, or smell dangerous, or feel dangerous. Fire is hot and bright. A predator is large and loud. A cliff is visibly far down. Our sensory systems evolved to detect and respond to exactly these kinds of threats, visible, immediate, proportionate to our perceptual scale. Deep space threats violate every one of these properties. Vacuum is invisible. You cannot see vacuum. You cannot smell it. You cannot feel it on the other side of the hull. If you did not have instruments telling you it exists, your senses would have no way of knowing it is there. Radiation is invisible, undetectable by human senses. A lethal dose of gamma radiation produces no sensation, no smell, no heat, no sound. The most dangerous radiation environments in the universe, the radiation belts of Jupiter, the corona of an active magnetar, are visually indistinguishable from the most benign. Your eyes tell you nothing. The cognitive damage from galactic cosmic rays accumulates over months and years. It does not feel like anything. Memory does not feel like memory getting worse. You simply remember less without noticing that you remember less. Cognitive speed does not feel like it slows. Things simply take slightly longer, and you do not notice the baseline shifting. The psychological deterioration of long-term isolation follows a similar pattern. It does not feel like deterioration. It feels like the situation simply being difficult. The gradual lowering of mood, the increasing interpersonal friction, the reduced capacity for humor and nuance. These do not come with a label saying this is psychological damage. They feel like the normal responses to a difficult situation. This is the most insidious feature of deep space threats. They are largely imperceptible. The environment does not announce its hostility. It does not look hostile. It looks like nothing. Empty, dark, silent. The damage is done quietly, below the threshold of sensation, measured only by instruments and by changes in function that may not be noticed until they are significant. On Earth, our threat detection systems are well matched to the dangers we face. In deep space, they are essentially useless. Every deep space threat is, from the perspective of human sensory systems, invisible. This means that the only way to know the environment is killing you in deep space is through measurement, through instruments, through data, through the kind of abstract knowledge that we have been talking about tonight, not felt knowledge, but known knowledge. And this creates a profound psychological challenge. Humans are evolved to respond to felt threats. Abstract threats, threats known but not felt, are much harder to respond to appropriately. This is why people smoke despite knowing the cancer statistics, why they eat unhealthily despite knowing the cardiovascular data. The abstract knowledge exists, but it does not trigger the visceral response that drives behavior change. Astronauts in deep space will know about the radiation. They will know about the cognitive effects. They will have seen the data. They will have signed consent forms. And then they will float in their habitats, experiencing nothing. No pain, no warning, no sensation, while the damage accumulates. This requires a kind of calm, sustained, data-driven self-awareness that is unusual in human psychology. The ability to respond appropriately to threats that are known but not felt, to trust instruments over sensation, to believe the numbers when your body is telling you nothing is wrong. Let us now talk about the specific category of threat that is hardest to prepare for, about novelty, and about what happens to human cognition when it encounters genuinely new situations. Human cognition is built on pattern recognition. We recognize situations by their similarity to previous situations and apply responses that worked before. This is extraordinarily efficient for navigating familiar environments. The problem is that it fails when genuinely novel situations arise, situations that have no precedent in the pattern library. The history of exploration is full of examples where explorers encountered situations for which their pattern libraries were completely inadequate and made catastrophic errors as a result. Not because they were unintelligent or ill-prepared, but because the situation was genuinely new. The first European sailors who crossed the Pacific had no patterns for the scale of that ocean. They made fatal miscalculations about distance because all previous sailing experience gave them a reference frame that simply did not scale to the Pacific. The first people to work with radioactive materials had no patterns for invisible, unfelt, accumulated radiation damage. They continued working in conditions that were destroying them because nothing in their sensory experience told them anything was wrong. The first pilots to fly into clouds without visual reference had no patterns for sustained spatial disorientation. They lost control and died because the vestibular system was giving them false information. and nothing in their pattern library told them to override it. Deep space will produce genuinely novel situations, situations for which no pattern exists. Not because the physics is unknown, we know the physics, but because the experiential reality of living in that physics has no precedent. What is it like to know with certainty that you cannot go home for 3 years? No simulation, no training, no Antarctic winter over fully replicates this. The knowledge can be prepared for intellectually. The experience cannot be simulated exactly, because the thing that makes it real is exactly that it is real, not that it will end in a few months when the experiment concludes, but that it actually will not end for 3 years. What is it like to watch your cognitive test scores gradually decline over months and know it is because galactic cosmic rays are damaging your neurons, and that you cannot stop it? No amount of exercise, no medication, no behavioral intervention fully prevents this. You can only reduce the rate of decline. The knowledge that the decline is happening and cannot be stopped is a psychological burden without earthly equivalent. What is it like to have a medical emergency? Appendicitis, a broken bone, a psychiatric crisis, in a context where the nearest hospital is months away and the nearest doctor is 40 minutes of signal delay from giving you a response. The protocols exist, the training exists, but the protocols and the training were designed on Earth for people with Earth's psychological and physiological state. A person who has been in deep space for 18 months, experiencing radiation exposure, sleep disruption, nutritional changes, and significant psychological stress, is not the same person who trained for this situation on Earth. These are not solvable problems. They are inherent features of the situation. They are what deep space is. The mission is to go anyway, understanding this, accepting this, managing this as well as possible, and go. Let us now talk about something that exists at the intersection of the very small and the very large, about what quantum mechanics says about the nature of the space you travel through and why this is its own form of deep strangeness. The universe operates on 2 frameworks: general relativity, which describes gravity, the large-scale structure of space-time, the behavior of massive objects, and quantum mechanics, which describes the behavior of particles at the smallest scales, the probabilistic nature of quantum states, the uncertainty at the heart of measurement. These 2 frameworks are each extraordinarily successful within their domains. General relativity predicted gravitational waves, ripples in space-time from merging black holes that were detected in 2015. Quantum mechanics makes predictions accurate to 12 decimal places in some experiments. Both are among the most precisely tested theories in the history of science. They are also mutually incompatible. The mathematical structures that describe quantum mechanics do not work in the curved space-time of general relativity. Attempts to combine them, quantum gravity, have produced interesting mathematics but no complete physical theory. This means that at very small scales, at the Planck scale, around 10 to the minus 35 meters, our understanding of space itself breaks down. We do not know what space is at this scale. We do not know whether space-time is smooth and continuous or grainy and discrete. We do not know what happens inside black holes, where quantum effects and gravitational effects are both extreme simultaneously. As you travel through space, you travel through something we do not fully understand at its most fundamental level. The practical physics works, the rockets work, the navigation works. General relativity is accurate enough for spacecraft trajectory calculations. But the deeper nature of the medium you travel through, what space actually is an open question at the foundations of physics. There is something specifically unsettling about this. We talk about travelling through space as though space is well understood, a known medium, just very large and mostly empty. And practically speaking, for all navigation and engineering purposes, it is well understood. But underneath the practical understanding, underneath the equations that work, there is a deep uncertainty about what space fundamentally is. The medium through which every interstellar journey would travel is, at its deepest level, not understood. This is a strangeness that cannot be resolved by building better instruments or collecting more data. It requires a new theoretical framework, a theory of quantum gravity, that, despite decades of effort from the smartest physicists on Earth, has not been completed. We are travelling through something we cannot fully describe. Let us now talk about the specific way that each horror we have discussed connects to a specific thing you can do, or see, or notice tonight. The magnetosphere. You cannot see the magnetosphere, but you can see its effects. The aurora, the northern or southern lights, are the visible signature of charged particles from the Sun spiraling along magnetic field lines into the polar atmosphere. If you live at sufficient latitude, above about 50 degrees north or south, you can sometimes see the aurora with the naked eye on clear nights when solar activity is elevated. When you see the aurora, you are seeing the magnetosphere working. You are seeing the thing that protects us. The charged particles that would otherwise gradually strip the atmosphere are being intercepted and guided harmlessly into a visible display. The horror they represent, the same particles that bombard unshielded astronauts on the Moon, becomes, at Earth's surface, beauty. The cosmic microwave background. You cannot see the CMB. It is microwave radiation, far below the frequency of visible light. But you can see its effect in a specific way. If you have an old analog television, the kind with a cathode ray tube, and you tune it between channels to static, about 1% of that static is caused by the CMB. Photons that have been travelling since 380,000 years after the Big Bang, crossing 13.8 billion years of cosmic expansion, landing on your television antenna and contributing to the hiss. The night sky itself. Every star you see is a sun, some smaller than ours, some larger, some vastly larger. Every star you see is in our galaxy. The nearest stars beyond our solar system are still within the Milky Way. The most distant objects visible to the naked eye are other galaxies, M31, Andromeda, at 2.537 million light-years, M33, Triangulum, at about 2.7 million light-years under very dark skies. When you look at M31, a faint smudge to the naked eye under dark skies, visible as an elongated glow in binoculars, you are looking at light that left 2.537 million years ago. When that light left M31, our ancestors were Homo habilis, using stone tools, not yet anatomically modern humans. The photons that you see tonight started their journey before our genus Homo existed. This is not a metaphor. This is what the sky actually is, not a backdrop, a time machine with depth. And somewhere in it, at the edge of naked eye visibility, invisible to you but known, is the direction of Proxima Centauri, the nearest star. 4.24 light-years. The nearest question, the nearest potential horror, the nearest potential hope, the nearest place we might someday send something, or someone, to find out what is there. Let us now talk about something that is both the most practically urgent and the most easily overlooked aspect of the journey through horrors we have taken tonight, about the timeline of when these horrors become real rather than hypothetical. Right now, the only humans in space are on the ISS. The threats at this first threshold are real and managed. Radiation limited by the magnetosphere, vacuum held at bay by hull and suits, bone loss slowed by exercise, psychological stress managed by rotation schedules and communication with Earth. The system works, imperfectly but functionally. In the 2030s, if current programs proceed, humans will return to the Moon. This is planned. The Artemis program has the stated goal of establishing a sustained human presence near the Moon. At this point, the second threshold threats become real. The unshielded radiation, the solar flare risk, the lunar dust, the communication delay now measured in seconds rather than milliseconds. In the 2040s or 2050s, optimistic timelines suggest crewed Mars missions. The third threshold threats become real. The impossibility of rapid return, the 26-month launch window constraints, the extended radiation exposure en route, the psychological burden of true isolation, the medical emergencies with no backup. Beyond that, the timelines become speculative. Interstellar missions are not planned. They are not technically achievable with current or near-term propulsion. The fourth, fifth, sixth thresholds we discussed remain theoretical threats for the foreseeable future. But the first three thresholds will become real within the working lives of people currently alive, possibly within the lifetimes of many people listening to this tonight. The horrors of deep space are not distant abstractions. Some of them are scheduled. Let us now talk about what I think is the single most important thing to understand about all the horrors we have described, about the relationship between knowing the danger and choosing to face it. Knowing is not the same as experiencing. We have spent this conversation in the realm of knowing, facts, numbers, mechanisms, predictions. You now know more about the specific ways deep space threatens human biology and psychology than most people on Earth. But knowing is cheap. Choosing is expensive. The people who will face these horrors, the astronauts who will walk on the Moon and feel the absence of the magnetosphere, the crew who will spend 3 years in deep space en route to Mars, the generation that might someday board an interstellar ship knowing the journey could alter their minds and their bodies permanently. They know all of this too. They know about the bone loss and the radiation and the cognitive decline and the psychological third quarter and the communication delay and the isolation. They sat in classrooms and read papers and heard lectures exactly like this one. And then they raised their hands and said they wanted to go. This is not stupidity. This is not recklessness. This is something older and stranger than either. It is the same thing that made some prehistoric human decide to follow game over a mountain pass into unknown territory, when the rest of the group stayed where it was safe. The same thing that made some individual in coastal Africa look at the ocean and wonder what was on the other side. The same thing that made Magellan's crew keep sailing west when every rational calculation suggested turning back. There is something in human nature that pulls toward the unknown, not despite the danger, but sometimes because of it. The danger is part of what makes the unknown worth knowing. The cost of going is part of what gives the arrival meaning. Every threshold we discussed tonight, every new kind of horror that emerges at each new distance, is a threshold that someone will someday cross, will have crossed if we extend the timeline far enough. And what they find on the other side will change what all the rest of us know about the universe. This is not nothing. This is everything. The horrors of deep space are real. The people who face them are choosing to face them with full knowledge of what they are. And the knowledge they bring back of what it is actually like to be there, not just what the physics predicts, but what the experience is knowledge that will change what it means to be human. We are an exploring species. We have always been. The gradient toward the unknown is built into us. And the universe, indifferent, vast, hostile in ways both familiar and unimaginable, has never once turned us back. Let us talk about something that is both deeply personal and universally relevant, about what the specific experience of looking at the night sky means once you understand what you are actually looking at. Most people look at the night sky and see beauty, stars, constellations, possibly the Milky Way if the skies are dark enough. This is real. The aesthetic experience of the night sky is genuine and valuable and needs no justification. But there is another way of seeing the same sky, not instead of the beauty, but alongside it. A way of seeing that comes from understanding what those points of light actually are. That bright, steady point you see, Jupiter, if it is visible tonight, white and unwavering, is a gas giant 318 times the mass of Earth, with storms that have raged for centuries, with a magnetic field 20,000 times stronger than Earth's, with radiation belts so intense that an unprotected human in Europa's orbit would die in 10 minutes. That reddish point you might see, Mars, if it is in the evening sky, is a place where the atmosphere is 100 times thinner than Earth's, where perchlorate salts in the soil are toxic to life as we know it, where the average temperature is minus 60 degrees Celsius, where global dust storms occasionally cover the entire planet for months. That pale, fuzzy smudge in the direction of Andromeda that you can barely see with the naked eye is a galaxy containing roughly 1 trillion stars, 2.537 million light-years away. The light you are seeing left it when our genus Homo did not yet exist. It is heading toward us and will collide with the Milky Way in roughly 4.5 billion years, a collision that will take hundreds of millions of years to complete and will rearrange the structure of both galaxies. That band of diffuse light across the sky, the Milky Way if you are under truly dark skies, is your view from inside a disk of roughly 100 to 400 billion stars. You are looking at it edge on. The center is in the direction of Sagittarius, that dense, bright region of the Milky Way visible in summer from the northern hemisphere. There, 26,000 light-years away, is a black hole 4 million times the mass of the Sun. Every direction you look at the night sky is a direction of potential horror at sufficient distance. In every direction, neutron stars spinning hundreds of times per second. In every direction, magnetars periodically releasing energies that would sterilize any planet within thousands of light years. In every direction, the faint signatures of supernovae that happened thousands of years ago, their remnants still visible as nebulae. In every direction, galaxies receding from us at speeds approaching light. And yet here, on this specific rock, at this specific distance from this specific star, everything is fine. The violence of the universe has not reached us in any form that prevents us from standing outside and looking up on a clear night. This is not guaranteed. It is a coincidence of conditions. The right distance from the Sun, the right magnetic field, the right atmospheric composition, the right position in the galaxy, far enough from the center that supernovae from dense star-forming regions don't sterilize us regularly, close enough that heavy elements were available for planet formation. The sky is simultaneously the most beautiful and the most honest thing we have direct access to. Looking at it requires nothing, no equipment, no training, no subscription. It is there every clear night for anyone who steps outside and looks up. And now that you know what it is different. Not less beautiful, but fuller, heavier, more honest. Let us now talk about a specific star you can find tonight that tells a specific story about one of the horrors we have discussed, about Betelgeuse and what it represents. Betelgeuse is the bright reddish star in the upper left of Orion, one of the most recognizable constellations in the northern hemisphere winter sky. It is a red supergiant. Its diameter is roughly 700 to 1,000 times the diameter of the Sun, so large that if placed at the center of our solar system, it would extend past the orbit of Mars. Betelgeuse is close to the end of its life. In astronomical terms, it will explode as a supernova in the next 100,000 years or so. In human terms, this could be tonight, or it could be 99,999 years from now. We cannot predict exactly when. When it explodes, it will be visible from Earth in daylight for weeks or months. At night, it will be bright enough to cast shadows. It will be one of the most dramatic astronomical events visible to the naked eye in Earth's history. Betelgeuse is about 700 light-years away. This is comfortably far. A supernova at this distance will be impressive to observe, but will not cause significant harm to Earth. Supernovae need to be within roughly 25 to 50 light-years to cause serious damage to Earth's ozone layer. At 700 light-years, Betelgeuse will be a spectacular show and nothing more. But look at it tonight, knowing what it is. A star so large that Earth would be a speck inside it. A star in the process of dying, accumulating iron in its core, each nuclear burning stage shorter than the last, approaching the moment when the core collapses and the outer layers bounce off and explode outward at a significant fraction of the speed of light. The light you see from Betelgeuse tonight left about 700 years ago, in 1325, when the 100 Years' War had not yet begun, when the Black Death had not yet arrived in Europe, when there were no European settlements in the Americas. Whatever Betelgeuse looks like tonight, that is what it looked like in 1325. It may have already exploded. If it exploded 699 years ago, the light from that explosion is on its way and will arrive in roughly a year. We would not know it was coming. There is no early warning signal that can outpace the light from the explosion itself. This is a specific, concrete example of the indifference of cosmic timescales to human awareness. The universe does not inform us of its events, it just does them, and we see them when the light arrives, on the universe's schedule, not ours. Let us now talk about a genuinely uplifting aspect of everything we have discussed, about what the human response to these horrors reveals about what we are capable of. The ISS is a place of extraordinary physical challenge. Zero gravity, high radiation, confinement, isolation from the immediate natural environment, and it is also one of the most productive scientific environments humans have ever created. Continuously inhabited since November 2000, more than 270 people from 20 countries have visited, more than 3,000 scientific experiments conducted. In the most hostile, accessible environment humans regularly inhabit, science continues, discovery continues, human cooperation across political and cultural divisions continues. The cosmonauts and astronauts who have inhabited the ISS have dealt with equipment failures, medical issues, interpersonal stresses, and the constant background of the physical challenges we have discussed, and they have continued to do their work. The Voyager probes, launched in 1977 with the computing power of a modern digital watch, are still operating, still transmitting data from beyond the heliosphere. Voyager 1 was designed for a 5-year mission. It is now 47 years old and still functioning. The engineers who built it are mostly retired or have died. Their work continues. Every large telescope, every spacecraft, every mission represents the accumulated effort of thousands of people working across years and decades toward a goal none of them will see fully realized alone. The Hubble Space Telescope was proposed in the 1940s, launched in 1990, and continues operating today, serving multiple generations of astronomers and producing discoveries its original proponents could not have imagined. The James Webb Space Telescope was proposed in 1989, launched in 2021, 32 years of work. It is now producing spectra of exoplanet atmospheres, detailed images of galaxies in the first billion years of the universe, and the most precise characterization of star-forming regions ever achieved. These are human achievements in the fullest sense. Not the achievement of one person or one generation, but the achievement of sustained collective effort across decades, across political changes, across budget cuts and engineering failures, and the deaths of key contributors. This is what we do when we encounter something vast and difficult and important. We organize, we persist, we build on what the previous generation accomplished. We tolerate the incompleteness of our own individual contributions because we understand they are part of something larger. The horrors of deep space are real. The response to those horrors, the engineering, the medicine, the psychology research, the materials science, the mission planning, is one of the most impressive, sustained collective achievements of our species. Let us now talk about what the specific exploration milestones ahead of us will actually feel like from a human perspective. Not in terms of engineering or science, but in terms of the lived experience of being there. The first human to stand on Mars and look up at the sky will see a sky that is not blue. The sky on Mars is a butterscotch or pinkish tan colour, caused by fine dust particles permanently suspended in the thin atmosphere, scattering red and yellow light. At sunset, the sky near the Sun turns blue, the opposite of Earth, where the sky is blue during the day and can turn red-orange near the horizon at sunset. They will see two small moons, Phobos and Deimos, moving across the sky visibly in real time. Phobos orbits so quickly that it rises in the west and sets in the east, completing an orbit in just over 7 hours. Deimos moves slowly, more like our moon, but much smaller. The Sun will be visibly smaller than from Earth, about 64% of its diameter as seen from Mars, noticeably smaller. The light will be dimmer and slightly more orange-tinged. The horizon will be closer than on Earth. Because Mars has a smaller radius, the horizon drops away sooner. The landscape will be geologically ancient. Most of Mars's surface is billions of years old, shaped by forces that ended long before complex life evolved on Earth. Craters, ancient river valleys, volcanic plains, the silence of a geological museum where the exhibits have been unchanged for longer than life has existed on Earth. And overhead, looking through a faceplate designed with extreme care to protect against radiation, against vacuum, against thermal extremes, they will see Earth, a bright blue star, not a disk, a point. The entire world of 8 billion people, their families, their cities, every place they have ever been, a point of light in a butterscotch sky. This is what the horror becomes at human scale, not a graph of millisieverts or a calculation of orbital mechanics. A human being in a suit on a red plane, looking up at a butterscotch sky, seeing their whole world as a point of light that takes 20 minutes to receive a message. This moment, when it happens, will be one of the most significant moments in the history of the species. Not because of the science it enables, though the science will be profound, but because a human being will be standing on another planet for the first time. Not floating in orbit around another planet, not flying past it in a spacecraft, standing on it, leaving footprints in its soil. After that moment, Nothing about who we are as a species is the same. We will be a species that has stood on two worlds forever. Whatever happens subsequently, we will have been that. The footprints on Mars will exist for millions of years in the absence of wind erosion, just as the Apollo footprints on the Moon still exist today. The terror and the wonder are the same thing. They cannot be separated. The butterscotch sky and the radiation are the same place. The tiny blue star that is home and the magnificent desolation of an ancient, unchanged landscape are the same view. This is what going further feels like. Not a series of escalating disasters, not a checklist of increasing horrors, but the expansion of the boundary of where humans have stood, at a cost that is real and chosen, into places that are simultaneously hostile and achingly beautiful. Let us now talk about the very specific thing that is happening right now, tonight, at this moment, that connects all of these abstract concepts to the immediate reality of your position in the universe. You are on a planet moving around a star at about 30 kilometers per second. The star is moving around the galactic center at about 220 kilometers per second. The galaxy is moving through the local group of galaxies at several hundred kilometers per second. The local group is moving relative to the cosmic microwave background at about 620 kilometers per second. At this moment you are in motion, in multiple nested reference frames, at speeds that would seem fantastical by any human terrestrial standard. You feel none of it. The motion is too smooth, the timescales too long, the reference frames too encompassing. At this moment, radiation is passing through you. Approximately 65 billion solar neutrinos pass through every square centimeter of your body every second. Cosmic microwave background photons fill every cubic centimeter of space around you, roughly 411 per cubic centimeter. Galactic cosmic ray particles are arriving at Earth's surface at a rate of about 1 per square centimeter per minute at sea level, attenuated enormously from their arrival at the top of the atmosphere by the atmosphere itself. At this moment, the Earth's magnetic field is deflecting a stream of charged particles from the Sun, the solar wind, that would otherwise interact with the upper atmosphere and gradually strip it away. The field is generated by convection of liquid iron in the outer core, a process that has been running for billions of years and shows no signs of stopping soon. At this moment, the ozone layer, a thin layer of O3 molecules between about 15 and 35 kilometers altitude, is absorbing ultraviolet radiation that would otherwise damage DNA at the surface. Without it, the UV flux at ground level would be roughly 1,000 times higher in the UVC range, sufficient to make the surface hostile to most surface life. All of this is happening right now, without any action on your part, without any awareness on your part. The planet and its systems are doing this for you, continuously, without pause. This is the context in which everything we have discussed tonight exists. Every horror of deep space is the absence of something the Earth provides. Every threshold we crossed was a threshold where something the Earth does for free, without announcement, without our participation, without our awareness, was removed. You cannot feel the magnetosphere. You cannot feel the ozone layer. You cannot feel the specific distance from the Sun that keeps water liquid. You cannot feel the gravity that calibrates your body. But they are there. They have always been there. Every moment of your life they have been doing their work. Going into deep space is going to a place where they stop doing that work, where the support systems that have sustained every moment of your existence simply are not there.
And the human response to this is not to stay home. The human response is to build suits and shields and ships and to go anyway. Because the other side of the fear is something that is also very human: curiosity. The need to see what is on the other side of the fear. The insistence that no horizon, however dark, however hostile, however indifferent, is a horizon that must stay unknown. This too is what we are. Look at the sky tonight. All of it is there. The beauty and the horror and the indifference and the history and the future. All of it, all at once. Every clear night for anyone who steps outside and looks up. And we are still going. Let us talk about something that connects everything we have discussed to a single concrete measurement, about what it would actually feel like to cross the heliopause, and why Voyager 1's crossing of that boundary in 2012 was one of the most significant events in the history of human exploration, even though almost no one was watching. August 25th, 2012. Voyager 1 crossed the heliopause, the boundary between the solar wind's influence and the interstellar medium, at about 121 astronomical units from the Sun. The crossing was not instant. It took months for scientists to confirm what had happened.
The data was ambiguous. The signals took over 16 hours to reach Earth. The scientists analysing those signals, a small team at JPL, were doing something no team had ever done before: reading data from beyond the solar system. The moment of crossing was not dramatic in the way space events often are in popular imagination. There was no explosion, no visible boundary, no alarm. The instruments on Voyager 1 simply began registering different values. The density of the plasma around it changed. The magnetic field orientation shifted. The flux of galactic cosmic rays, previously partially moderated by the heliosphere, increased sharply. And that increase in cosmic ray flux was the confirmation. Beyond the boundary, the full, unmediated flux of galactic cosmic rays. The same particles we discussed earlier, iron nuclei, accelerated to relativistic speeds by supernova explosions billions of years ago, arriving from all directions with brutal uniformity. The same particles that, if a human were present at Voyager 1's location rather than a 722-kilogram spacecraft, would be accumulating in their brain tissue at rates we cannot fully protect against. Voyager 1 is the furthest human object from Earth. It was launched 47 years ago. It will never come back. It is now moving through the interstellar medium, the space between stellar systems, at about 17 kilometers per second, in the general direction of the constellation Ophiuchus. In about 40,000 years, it will make a close approach to a star called Gliese 445. In about 296,000 years, it will pass near the star Sirius. No human will ever follow Voyager 1, not with current technology, not with any technology we can describe building within a century. The gap between Voyager 1 and the next human-made object to reach the interstellar medium, if one is ever sent, will be measured in decades at minimum. The gap between Voyager 1 and the first human to travel through the interstellar medium, if one ever does, will likely be measured in centuries. We cross that threshold by proxy, with a machine. And even by proxy, even with a machine, even with no humans present, the crossing revealed something new. The interstellar medium was different from what models predicted in specific ways. The magnetic field direction was different. The cosmic ray spectrum was slightly different from expected. The actual boundary of the heliosphere turned out to be complex rather than clean. This is always how it works. The place is always different from the model. The model is necessary. It gets you there. It tells you where to look. It gives you the framework for interpreting what you find. But the place, being real, is more specific and more complex and more surprising than the model. This will be true for Mars. It is already true for the Moon, where the specific texture of the regolith and the specific behavior of lunar dust and the specific dynamics of the lunar exosphere all turned out to be more complex and more challenging than pre-mission models predicted. It will be true for every subsequent threshold. The place is always richer than the preparation for it. The horror is always more specific than the general description, and the wonder always is more immediate than anything described from a distance. Let us now talk about a specific and underappreciated aspect of the horror of deep space, about the specific relationship between distance and the concept of meaning. On Earth, distance is bridgeable. 10,000 kilometers is a long flight, but not a conceptual barrier. You can call someone 10,000 kilometers away and speak in real time. You can know that someone on the other side of the planet is experiencing something simultaneously with you. The world is synchronous in a way that human psychology evolved to manage. The concept of simultaneity, the sense that right now things are happening across the world that are connected to your right now, is deeply embedded in human psychology and in human meaning-making. Events have significance partly because they are happening now. News is relevant because it describes what is happening in a shared present. At light-minute distances, Mars, this begins to break down. There is no shared present. The Mars colony's present and Earth's present are separated by up to 22 minutes of signal delay. Something happening right now on Mars is, from Earth's perspective, something that happened between 3 and 22 minutes ago. There is a delay between the universe's events and our knowledge of them. At light-year distances, Proxima Centauri, there is no meaningful simultaneity at all. What is happening at Proxima Centauri right now is completely inaccessible. The only thing we know about Proxima Centauri right now is what it looked like 4.24 years ago. We live in the Proxima system's past, and the Proxima system lives in our past simultaneously. Neither of us can access the other's present. This is not just a communication delay, it is a philosophical rupture. The concept of a shared universe, a universe in which events at different locations are part of the same simultaneous reality, is not how the universe actually works at these distances. The universe does not have a shared present at interstellar scales. It has a network of overlapping pasts, each accessible only through the light that left it and travelled to reach you. For a crew on an interstellar ship, this creates a specific experience of reality. The Earth they left is not the Earth that exists now. The Earth that exists now, 4.24 years in their future, is inaccessible. The messages they receive from Earth are messages from Earth's past.
The messages they send will arrive at Earth's future. They live in a permanently displaced relationship with everything they knew. This is a form of isolation that is not spatial, but temporal. And it deepens with distance, at 4 light years separated by 4 years of inaccessible present, at 100 light years separated by a century, at 1,000 light years separated by a millennium. The further you go, the more fully you leave not just the place, but the time. You become a traveller not just in space, but in the permanent displacement of what the universe calls now. Let us now talk about something that is rarely articulated, but becomes clear when you think about the full scope of the journey we have taken, about the specific way that each threshold changes not just the physical danger, but the philosophical framework within which danger exists. At the first threshold, low Earth orbit, danger exists within a familiar framework. Things can go wrong, people can be hurt, rescue is possible. The category of danger is recognizable from Earth experience: accidents, equipment failure, medical emergency. At the second threshold, the Moon, the framework begins to shift. rescue is possible but slow. The radiation is invisible and unfelt. The specific cause and effect chain between the flare and its consequences stretches over hours. The danger is becoming more abstract, less immediately visceral. At the third threshold, Mars, rescue is impossible in any reasonable time frame. The framework of safety net has collapsed. There is no net. You are managing the risks directly, all the time, with no backup system that can respond quickly enough to matter in most emergency scenarios. This is a different relationship with danger, not danger that can be rescued from, but danger that must be managed continuously with no external help available. At the fourth threshold, beyond the heliosphere, the danger becomes cumulative, invisible, and essentially unavoidable.
The galactic cosmic rays cannot be fully shielded. The cognitive damage they cause is slow, unfelt, and irreversible in part. The framework of avoid the danger or treat the damage has transformed into accept some inevitable damage and minimize what can be minimized. At the fifth threshold, the intergalactic void, the framework collapses entirely. There is no rescue, no backup, no gradual management of risk. There is only the ship and what it carries and what happens. No structure outside the ship has any relevance to the ship's survival. The universe is not hostile in the way that it was at closer distances. It is simply absent. And absence at sufficient scale is its own category of threat. The threat of there being nothing, no help, no resources, no context, no possibility of any kind of intervention from outside. At the cosmological threshold, at the horizon of the observable universe, the framework of danger no longer applies in any human sense. There is nowhere to go beyond the horizon because beyond the horizon is not accessible. It is not dangerous. It is simply outside the category of things that can be experienced. And at the final threshold, the heat death, the framework of danger ceases to apply because there is no longer anything that can be endangered. Danger requires something that can be destroyed. The heat death destroys the very category of destroyable things. Each threshold does not simply add more danger to an existing framework. It changes the framework itself. It redefines what danger means, what rescue means, what safety means, what existence means. The journey through the horrors of deep space is a journey through progressively more radical philosophical transformations of the basic concepts through which we understand ourselves in a universe. At the end of the journey, there is no journey, there is no traveler, there is no universe that anyone can be lost in. Just equilibrium. Absolute, permanent, universal equilibrium. Let us now talk about the specific thing you can do tonight that connects directly to one of the most important unresolved scientific questions about deep space, about looking for the aurora and what it tells you about the magnetosphere that protects us from one of the horrors we discussed. If you live above roughly 50 degrees north latitude, northern Canada, Scandinavia, northern Russia, Scotland, Alaska, you have the possibility on any clear night of seeing the aurora borealis. The necessary conditions: a clear sky, a night without too much light pollution, and some level of solar activity creating a geomagnetic storm at Earth. The aurora is the visible evidence of the magnetosphere at work. Charged particles from the Sun, protons and electrons in the solar wind, are captured by the magnetic field and guided along field lines toward the polar regions, where they collide with atmospheric molecules. The oxygen molecules emit green light, most commonly, at about 100 kilometers altitude, and red light at higher altitudes. Nitrogen produces blue and purple hues.
What you are seeing when you see the aurora is the interaction between the sun's output and Earth's defense system. You are seeing the magnetosphere doing exactly the work that prevents the surface of Earth from becoming the surface of the Moon, gradually stripped of atmosphere, exposed to the full flux of solar radiation. The same particles that produce the beautiful green curtains in the polar sky are the particles that would, without the magnetosphere, be striking the upper atmosphere and ionizing it and stripping ions away into space over geological time. Mars lost its magnetosphere roughly 4 billion years ago. After that, the solar wind gradually stripped the Martian atmosphere, the same process that creates aurorae on Earth without the magnetic protection to constrain it. Today, Mars has a thin atmospheric remnant.
Before the loss of the magnetic field, it may have had a thicker atmosphere and possibly liquid water on its surface. The aurora is beautiful. It is also a reminder of what makes beauty possible here, the invisible infrastructure of a functioning magnetosphere that we inherited from the Earth's formation and have never had to think about. Look for the aurora if you're in the right latitude, or look it up. There are real-time aurora forecasts and webcams from Norway, Iceland, Alaska, Canada that show it live. Watch it knowing what it is, the magnetosphere working, Earth's defense system made visible. Let us now talk about one more specific thing, about what becomes possible when you hold all of this knowledge at once and look at the night sky with it. The sky is not a flat backdrop. It is a volume. It has depth, enormous, almost incomprehensible depth. And within that depth are objects of every kind we have discussed tonight.
The nearby objects, the Moon, the planets, are places where the first thresholds of horror exist. Reachable, in principle, within human lifetimes with human technology, the nearby stars, within 50 or 100 light years, are where the fourth and fifth thresholds live, places where the full unmediated flux of interstellar radiation exists, where the dust of the interstellar medium flows, where no stellar system has provided any particular shelter. The distant stars, thousands to tens of thousands of light years, are where the events we discussed as extreme horrors happen. Supernova explosions creating neutron stars, magnetar starquakes, gamma-ray bursts. These events are happening right now in the galaxy. We see them, delayed by the time light takes to reach us, as events in our sky. The galaxies, millions to billions of light years, are where the sixth threshold lives.
The intergalactic voids between them, the filaments of dark matter connecting them, the expansion of the universe carrying them away from us. And at the edge of what is visible, at the furthest redshifts, is the seventh threshold, the horizon of the observable universe, the limit of what can be seen from here by any instrument using any wavelength of light. When you look at the sky, you are looking into all of this simultaneously. The Moon at 1.3 light seconds, Betelgeuse at 700 light years, M31 at 2.537 million light years, quasars at billions of light years, the cosmic microwave background at 13.8 billion light years, or more precisely, at the distance that light has travelled since the universe became transparent, which, due to expansion, now corresponds to about 46 billion light years. All of it is there. All of it is real. All of it is subject to the physics we have been describing. And in the middle of all of it, on a small, rocky planet, under a blanket of nitrogen and oxygen and ozone, inside a magnetic bubble generated by a churning iron outer core, at the precise distance from a medium-sized G-type star to keep water liquid, you are standing outside looking up. The horror and the beauty are inseparable. The fragility and the protection are inseparable. The unknown and the known are inseparable. Deep space gets more horrifying the further you travel, and the further you understand how horrifying it gets, the more remarkable it becomes that we are here at all, protected from most of it by a planet that has never asked anything of us in return. Let us talk about something that is both scientifically specific and deeply personal, about what the discovery of gravitational waves in 2015 revealed about a category of horror in deep space that we had only theorized about before. On September 14th, 2015, at 5:51 a.m. Eastern Time, the two LIGO detectors in Hanford, Washington and Livingston, Louisiana, simultaneously registered a signal, a chirp, a brief oscillation that lasted about 0.2 seconds. A pattern that matched what physicists predicted would be produced by two black holes merging. The signal was caused by a merger of two black holes, one about 36 solar masses, one about 29 solar masses, that occurred about 1.3 billion light-years away. They had been orbiting each other for billions of years, spiraling inward, losing energy through gravitational wave emission. In their final fraction of a second, they were orbiting each other dozens of times per second, moving at a significant fraction of the speed of light, distorting the space-time around them into waves that spread outward at the speed of light. When those waves reached Earth 1.3 billion years later, they stretched and compressed space by about 1/1000th the diameter of a proton. Over the 4-kilometer arms of the LIGO detector, this is the most precise measurement in the history of science. What this means for the horror of deep space. Space-time itself is not rigid, it can ripple. Massive objects moving at relativistic speeds, merging black holes, merging neutron stars, distort the very fabric of space as they do so, and those distortions travel outward as gravitational waves. A gravitational wave passing through you right now, which one almost certainly is from some distant merger, is stretching and compressing the space your body occupies at a rate far below the threshold of any sensation. The LIGO detectors are among the most sensitive instruments ever built, and they can barely detect these waves from the mergers they are sensitive to. But if a merger happened much closer, close enough for the gravitational waves to be strong enough to physically affect macroscopic objects, the effects would be very different. The distortion of space would be strong enough to stretch and compress objects, including biological objects, cyclically as the wave passed. The frequencies involved in the final merger, the chirp, are in the audio range. The human body would be physically oscillated. At what distance would this become harmful? It depends on the masses involved. For stellar mass black hole mergers, comparable to what LIGO detected, you would need to be extremely close, on the order of astronomical unit distances, before the gravitational wave amplitude became physically significant. This is not a practical threat for any known merger. But extreme events, the merger of supermassive black holes, the kind that happen in the cores of galaxies when two galaxies merge, produce gravitational waves vastly more powerful. The merger of 2 billion solar mass black holes would produce waves strong enough to be relevant at significantly larger distances. The deeper point is not the immediate threat. It is the revelation. Gravitational waves showed us that space-time is dynamic, not a passive container in which events occur, but an active participant that can ripple and distort and carry energy across billions of light years. The medium through which all space travel would occur is not inert. It has its own modes of vibration. It can be disturbed by the most violent events in the universe and carry those disturbances outward at the speed of light.
We have been talking about threats to travelers in space. Gravitational waves reveal that space itself can be threatened, that the geometry of the universe is not fixed but dynamic and participatory. Let us now talk about a category of deep space horror that is unique because it is not a threat to travelers. It is a threat to the concept of knowledge itself, about the information loss paradox and what it suggests about the fundamental limits of what can be known.
When matter falls into a black hole, it crosses the event horizon and is lost to external observers forever. The information about what fell in, its quantum state, the specific arrangement of particles that made it up, is gone from the observable universe by classical general relativity. This is deeply troubling for quantum mechanics. Quantum mechanics is built on the principle of unitarity, the principle that quantum information is conserved. The total information content of a closed quantum system does not change over time. It can be scrambled and rearranged, but it cannot be destroyed. If information is genuinely destroyed when it falls into a black hole, quantum mechanics is wrong. If quantum mechanics is right, the information somehow survives. But how? Stephen Hawking proposed in 1974 that black holes are not completely black. They emit thermal radiation, now called Hawking radiation, due to quantum effects near the event horizon. Eventually, a black hole evaporates completely through this radiation. But Hawking's original calculation suggested the Hawking radiation is perfectly thermal. It contains no information about what fell in. If that is correct, the information is indeed destroyed when the black hole evaporates. This is the black hole information paradox. The debate between Hawking and others about whether information is truly destroyed or somehow encoded in the Hawking radiation has been one of the central tensions in theoretical physics for 50 years. It requires resolving the conflict between general relativity, which says information is lost, and quantum mechanics, which says it cannot be. This is exactly the conflict that requires quantum gravity, the theory we do not have. In 2023, Hawking himself, before his death in 2018, he had revised his position, and subsequent work by Juan Maldacena and others, using the ADS/CFT correspondence, a specific duality between certain quantum gravity theories, suggested that information is not lost. It is encoded in the Hawking radiation in a highly scrambled, practically inaccessible form. The information is preserved, but completely uncuttable. This suggests a universe in which fundamental information is conserved. Nothing is ever truly lost, but where the information can become so scrambled as to be for all practical purposes unrecoverable. What does this mean for the horror of deep space? In a practical sense, nothing. Travelers do not fall into black holes casually. But in a philosophical sense, it means that the universe at its deepest level keeps perfect records. Every particle that has ever existed, every quantum state that has ever obtained, somewhere in the universe's wave function, this information persists, even after the black hole that ate it evaporates. This is both comforting and unsettling. Comforting because it suggests an ultimate conservation, nothing is truly gone. Unsettling because the universe keeps these records in forms that are theoretically accessible but practically unreachable. The information exists but might as well not, for any purpose of recovery or use. The universe is a perfect information keeper and a perfect information scrambler. Let us now talk about a specific and deeply human aspect of everything we have covered, about the role of wonder in the experience of space, and why wonder is not separable from horror in the context we have been discussing. Edmund Burke, the 18th century philosopher, distinguished between two aesthetic experiences, the beautiful and the sublime. The beautiful is pleasant, approachable, orderly. The sublime is vast, overwhelming, potentially terrifying, but producing in its contemplation an experience of elevation precisely because of its power. Burke specifically identified the sublime with things that could cause harm: vast spaces, darkness, great heights, thunderstorms. things that in direct encounter would be dangerous, but in safe contemplation produced a specific aesthetic pleasure that the merely beautiful could not. Deep space is the most sublime object of contemplation available to the human mind. Not merely large, not merely distant, but actively challenging, threatening at the specific threshold where encounter becomes real, while simultaneously producing, in the informed contemplation of what it is, an experience that has no competitor for scale and significance. Every horror we have discussed tonight is simultaneously an object of wonder. The radiation belts of Jupiter that would kill you in minutes are also among the most powerful natural particle accelerators in the solar system, studied for what they reveal about plasma physics and magnetic confinement. The galactic cosmic rays that gradually damage neurons are also evidence of the most violent events in the universe: supernova explosions, neutron star mergers, perhaps the termination shocks of supermassive black holes that accelerated them to these energies billions of years ago. The heat death of the universe, the most final and most complete of all the horrors, is also the endpoint of a trajectory whose beginning was one of the most extraordinary events imaginable, a point of unimaginable density and temperature from which everything that exists emerged in the first fraction of a second of time. The universe's story from that beginning to this end is the largest narrative in existence. And the fact that there is a thing, a human mind, that can contemplate this narrative from inside it, that can look at the sky and understand that what it sees is not decoration, but depth, not backdrop, but structure, not silence, but physics operating at scales that overwhelm intuition. This is its own form of wonder. We are made of stellar debris. Every atom of carbon in your body was forged in the nuclear furnace of a star that exploded before our sun formed. The iron in your blood was synthesized in a supernova. The oxygen you breathe was produced by generations of stars burning hydrogen and releasing it into the interstellar medium over billions of years. We are the universe contemplating itself, made of its own substance, assembled by its own processes, now turning to look at what made us and finding it vast and cold and indifferent and magnificent. The horror and the wonder are not in tension. They are the same thing viewed from different angles. Let us now talk about what the future of deep space exploration will actually look like. Not in the far speculative sense, but in the near practical sense. About what the next 50 years of human expansion into space will actually require. The immediate practical requirement is better radiation protection. Not complete protection. Complete protection against galactic cosmic rays is probably not achievable with passive shielding at any practically deployable mass, but better protection than we have now. Active shielding concepts, generating magnetic fields around the spacecraft to deflect charged particles, analogous to the Earth's magnetosphere, are being researched. Pharmaceutical countermeasures, drugs that reduce radiation sensitivity or promote DNA repair, are being explored. Diet-based interventions with antioxidants that reduce radiation damage are being studied. None of these is a solution. Each reduces the problem somewhat. The combination of improved active shielding, pharmaceutical support, and better passive shielding materials may reduce the radiation exposure of a Mars crew to a level that NASA considers acceptable. This is the goal for the next 20 to 30 years. Better life support. The ISS recycles about 93% of water from sweat, breath, and urine. For Mars, recycling rates of 98 to 99% are needed. The systems must operate reliably for years without replacement parts. This requires redundancy, repairability, and materials that do not degrade under long-term use. In-space manufacturing, 3D printing, is part of the solution for producing replacement parts. Better food. Stored food degrades over years, especially under radiation exposure. Vitamins degrade. Some amino acids break down. Growing food in space, small hydroponic systems, provides fresh nutrition and psychological benefit. A Mars mission needs enough variety and nutritional completeness to sustain the crew for 3 years without significant deficit. Better medicine. A small crew far from Earth needs to handle medical emergencies that on Earth would require specialist intervention. The crew needs training, equipment, and AI-assisted diagnostic support, robust enough to manage the most likely medical scenarios. Telemedicine with a 40-minute round-trip delay is not the same as telemedicine with instant communication. The crew needs to be able to make decisions without waiting for advice. Better psychology. Crew selection that prioritizes interpersonal compatibility as much as individual competence. Communication programs with Earth designed to maintain emotional connection through the delay. Structured psychological support at the mission level, scheduled psychological assessments, access to counselors via pre-recorded sessions and asynchronous messaging, planned activities that break the monotony of the mission without disrupting operations. All of these requirements are known. The research programs are running. Progress is real. In 20 to 30 years, if funding and priority are sustained, we may have crews technically capable of making the Mars mission in conditions that are significantly safer than today. Significantly safer. Not safe. There is no safe Mars mission with any technology we can imagine building. There is only safer. And the choice will be made by the people who go, whether the significantly safer is safe enough for what is on the other side. It has always been made that way, by the people who chose to go. Let us now talk about a specific and rarely articulated truth about the horror of deep space that brings everything together. About how the deepening horror at each threshold is not separate from the deepening knowledge that made the horror visible. A century ago, the specific horrors of deep space were not known, not because they did not exist, because we had not yet built the instruments to detect them, the theory to describe them, the missions to measure them. The galactic cosmic rays that damaged the brain, we did not know this in 1950. We suspected ionizing radiation was harmful. We did not have the specific understanding of how high-energy ion nuclei interact with neural tissue, how the hippocampus responds to heavy ion radiation, what the behavioral consequences of specific brain region irradiation are. The SANS syndrome, the vision changes that affect astronauts, was first systematically described in the 2010s from ISS data. It was not known before humans spent long periods in microgravity. The knowledge came from the experience. The psychological patterns of isolation, the third quarter effect, the interpersonal dynamics of confined crews, the specific ways that communication delay affects emotional well-being, were documented through polar expeditions, submarine missions, simulated space missions. This knowledge is recent. It is the product of deliberately studying humans in extreme conditions. What this means. Every horror we described tonight is a horror that was earned, not handed to us, not revealed by simple reflection. Earned through decades of instruments, experiments, missions, papers, arguments, revisions. Through the hard work of thousands of scientists, engineers, and physicians who cared enough about the truth to spend their careers figuring out exactly what is out there and exactly what it does to human bodies. The horror is not separate from the knowledge. It is the knowledge. To know that deep space gets more dangerous the further you go
is not a reason for despair. It is the product of one of the most sustained and disciplined intellectual efforts in human history. The effort to understand the universe we live in, with enough precision to go somewhere in it without dying. And the knowledge, in addition to being frightening, is useful. It is the foundation of every protection, every countermeasure, every medical protocol for future missions. You cannot protect against what you do not understand. The horror, precisely described, is the first step toward the management of the horror. This is what science does. It turns the unknown into the known. It turns the formless darkness beyond the horizon into a map. Not a safe map, there is no safe map of deep space, but an honest one. A map that says exactly what is out there and exactly what it will do and exactly what it will cost. We are drawing that map, one mission, one experiment, one paper at a time. And the map, terrifying as it is the most valuable thing we have produced, because without it, we cannot go. And we are going to go. Go outside tonight. Look up. Find one star, any star. It does not matter which one. The first one you see when you look up is sufficient. A point of light that has been traveling for years or decades or centuries to reach your eyes at this specific moment. Now think about what stands between you and that star. Not the distance. You know the distance is enormous. Not the cold. You know it is cold in ways that make the word cold meaningless. Think about something more specific. Think about what is not there. Between you and that star, there is no magnetosphere. The shield that has surrounded Earth for billions of years, that deflects the solar wind, that makes the aurora in the north and south, stops at about 60,000 kilometers in the direction of the star. Beyond that boundary, the full flux of the solar wind. The same particles that produce those curtains of green light in polar skies stream unimpeded through interstellar space toward anything in their path. Between you and that star, there is no atmosphere. The layer of nitrogen and oxygen and ozone that you breathe right now, that absorbs the ultraviolet that would otherwise damage your DNA, that maintains a pressure against which your cardiovascular system was calibrated over millions of years of evolution, it ends about 100 kilometers above your head. Beyond that, the pressure approaches zero. You carry your atmosphere with you in your lungs, and it lasts about 15 seconds without replenishment. Between you and that star, there is no gravity calibrating your body. The gravitational field that signals your bones to maintain their density, that keeps blood from pooling in your head, that gives your cardiovascular system the resistance it evolved to work against, it decreases with the square of distance. By the time you reach the orbit of Mars, it is already less than half of 1% of what it is here. Your skeleton begins losing density from the first day in weightlessness. Your heart begins to shrink. Your vision begins to change as fluid redistributes toward your head. Between you and that star, there are galactic cosmic rays. Iron nuclei accelerated by supernova explosions to velocities approaching the speed of light, arriving from all directions with brutal uniformity, penetrating any practical shielding, passing through the brain and depositing energy along their tracks in ways that gradually and silently damage the neurons that form memory and regulate judgment and maintain cognition. The damage accumulates. It is not felt. It cannot be fully prevented. Between you and that star, there is the interstellar medium. Rarefied gas and dust that at the speeds required for interstellar travel becomes a continuous flux of ionizing radiation on the forward surface of any ship. Dust grains a few microns across carry, at 20% of the speed of light, kinetic energy equivalent to small explosions. The faster you go, the worse this becomes. Between you and that star, at distances of millions of light years, is the intergalactic void. 1 hydrogen atom per 10 cubic meters. Nothing for millions of light years in any direction. Temperature approaching absolute zero. No rescue, no resources, no context. No possibility of any external help of any kind. Just the ship and whatever it carries, and the silence of the most empty places in the universe. And beyond that, the expanding geometry of space-time itself. The horizon of the observable universe receding at the speed of light. The structure of reality making certain destinations not merely difficult, but geometrically impossible. And at the very end of everything, not a destination, but a condition, the heat death. The slow, inevitable, absolute cooling of the universe toward maximum entropy.
Every star burning through its reserves, every black hole evaporating through quantum radiation, every structure dissolving into thermal equilibrium. The universe arriving, after 10 to the 100th years, at the perfect stillness it has been trending toward since the moment it began. All of this stands between you and that star. All of it is real. All of it is there right now. And yet, we are going. Not despite the knowledge of what is out there, because of it. The astronauts who will climb into rockets in the coming decades know the radiation numbers. They have read the papers on cognitive decline from galactic cosmic ray exposure. They have seen the data on bone density loss, on SARS, on the psychological third quarter effect, on the communications delays, on the absence of rescue options beyond certain distances. They have sat with flight surgeons and signed consent forms that describe the biological costs in clinical language. And they will go. Because the knowledge that makes these horrors visible is the same knowledge that makes the destination meaningful. You cannot separate the horror from the understanding that produces it. You cannot want to know what is out there and simultaneously refuse to know what is between here and there. The universe does not offer that bargain. The people who go carry the full weight of what is out there, not in their luggage, but in their understanding. They go informed. They go consenting. They go knowing that some fraction of what they are will be left behind in the radiation and the weightlessness and the years away from everything their biology was built for. And they go because what is on the other side, the knowing, the being there, the specific reality of a world that no human has ever touched, is worth the cost. This is not irrational. This is the most deeply human calculation there is. The same calculation that was made by every person who ever crossed an unknown ocean, who climbed an unclimbed peak, who entered a cave where no one had been before. The value of knowing weighed against the cost of getting there. The universe makes the cost real. It does not negotiate. It does not offer discounts or shortcuts. It charges exactly what the physics demands, not a millisievert more, not a millisievert less. And we pay it. In the bodies of the people who go. In the years of their lives that are different after the mission than they would have been without it. In the small but real biological costs that accumulate with each mission further from the protection of this specific planet. Look at that star again. The light you are seeing left it years ago, maybe decades, maybe centuries. It traveled in a straight line through all of that, through the vacuum and the radiation and the cosmic rays and the interstellar dust, and landed on your eye at this specific moment in your life. You are receiving a message from deep space right now. Every photon of starlight is a message that has traversed everything we have talked about tonight and arrived somehow here. The universe is not silent. We are just learning to hear what it says. Tomorrow, or next year, or in the decade after that, some of us will go further into what it is saying. We'll travel outward through the first threshold, the second, toward the third. We'll carry instruments and suits and years of preparation and the knowledge of exactly what is out there and exactly what it will cost. They will pay the cost. They will come back changed. And what they find, what they bring back in data and in understanding and in the specific memory of having been somewhere no human has been before, will change what all the rest of us know about the universe. This is how the map gets drawn, step by step, threshold by threshold, at a cost that is real and a knowledge that is worth it. Go inside tonight, knowing what is out there, and knowing that it has never once turned us back.